look at them. Hopefully you can read them. I know I go off in the black part. You guys can move if you want to. Don't have to, but you can. All right. So in general, Kc, the equilibrium constant, the expression is the concentration of the products raised to their coefficient over the concentration of the reactants raised to their coefficient. I want to point out one thing. If I'm looking at, any questions on what I have written so far? You good? If I look at this system, bless you. So those are all gases. It's not typical that we measure the concentration of a gas in molarity. Anybody have any idea what we usually measure gases in? Going back to the gas chapter, back in quantitative. Okay. We normally measure them in pressures. All right? And if I have a bunch of gases in one system, anybody remember?
It was like the combined pressure.
Yes, combined pressure, the total pressure, yes.
Dalton's law.
Dalton's law, right? Dalton's law says the total pressure of that vessel is going to be equal to the sum of, which are called what? The individual pressures are called the partial pressures. Beautiful. Okay, so normally when we're talking about a gas system, we're going to measure their concentrations in partial pressures. Whereas this, what I've written so far is a Kc. You can also write them using what is called a Kp. It should be a capital K, by the way. Kp. And this is really used just for gas systems. Yes, Noel?
Wait, in the book, they wrote all of them with the EQM on, like, for the first part, they wrote all the EQMs after the...
Oh, after the thing. That just says that all those concentrations are at equilibrium.
Okay, so is that necessary?
No, we're going to, no.
Okay.
Technically, probably, but no.
Just making sure.
Yeah, no. Because if you're writing a K, it's at equilibrium. So it's by definition the concentration at equilibrium. Okay, good question though. So I would write, instead of just using the molarity symbols, you write the partial pressure of hydroiodic acid, and then you just put the partial pressure, square that. Oh, the purple doesn't show up well at all, does it? Let's change it to yellow. All right, so P of HI squared. That's a little better, right? Okay, and then the partial pressure of hydrogen and the partial pressure of the iodide. Both to the first power because they're ones in the coefficients. So there's a Kc. Yes, Lily?
I just have a question about equilibrium in general.
Mhm.
Will it always be like an elementary step, or are there any equations that are equilibrium without a step following?
There are equilibriums that are actually mechanisms, but you still write overall the expression is using the concentrations to the powers. Okay? All right, so we've had a Kc, a Kp. Just to give you a heads up, there are also things like there's a Kc, there's a Kp, there's a K equilibrium, which is probably the most general. There is an equilibrium constant for acids. So I've got one for acids. You think I have one for bases? Yep. And then there is also one for the solubility product. That's just a few of them. All right. So don't think that it's just Kc or just Kp. There's Kas, there's Kbs, there's Keq, which is generally what all of them are. All right. So they are specific equilibrium constants. So they say it's a constant. So it never changes. It's like the gas constant. Getting some head shaking, no. When would my equilibrium constant change, the value? Noel? Good, when the temperature changes. Because really, this equilibrium constant is a combination of the rate constants. Okay, because we're talking about the rate forward, the rate in reverse. And when does the rate constant change? Only when I change the temperature. All right, so the equilibrium constant is constant for a system at a given temperature. This is not where I want to be. Hang on for just a sec. Don't know exactly how to get to where I want to be. This is the next one on yours, right? All right, so if we look at this problem, equilibrium constant for the reaction of N2 to O2 gives me the value of, gives me, there we go. Gives me a value of, I wish my other stuff worked. Kc is 10 to the negative 30th. And then I flip the equation and they're asking me for the new value. All right. What I'd like you to do is write the Kc expression for this first equation. And we just did a bunch of them, so hopefully you can tell me that it's going to be nitrogen monoxide squared over the nitrogen concentration over the oxygen concentration. Yes? So now looking at the second equation, what's its equilibrium constant expression? Concentration of N2 over O2, so it's a concentration of the products over the concentration of the reactants raised to their power. Yes? Oh. What do you notice about those two expressions? Yeah, they just flipped. Oh. So when I flip an equation, what do you think I have to do to the value of that equilibrium constant? I take its, the inverse, the reciprocal of it. Oh, okay. So this would be 1 over 1 times 10 to the negative 30th, which is 1 over 1 times 10 to the 30th. Oh, okay.
Wait, no, it's not. Wouldn't it be 1?
Oh,
just
yep.
Plain? Yeah.
That's really messy, isn't it? Thank you, Nick. So I have a question. That all makes sense, right? You see it like that, you go, that's why, if you're caught up or a little bit above. Now, this Kc for my original, is that much greater or much less than 1? 10 to the negative 30th? It's much, much smaller, yes? So it's much smaller than 1. So if we look at that expression, does that mean, what does that mean? Looking at this expression, what does it mean that this number up here is? Is that number very big or very small? Very small, right? That's the concentration of the products, right? Conversely, that means this number is probably pretty big, yes? That's the concentration of the reactants. So what do I have present in greater amounts, the reactants or the products? The reactants. Oh, so if my K is much, much smaller than 1, then my equilibrium is said to lie to the left or lie to the reactant side, right? I like to say lie to the reactant side because sometimes I flip my left and right. Shh, don't tell anybody. It's going to be on YouTube shortly. All right, so now if I flip that equation like they did in this problem, now my Kc is much greater than 1, right? So that means my equilibrium lies to the product side, meaning I have a higher concentration of products than reactants. That all make sense? Yay! You guys are so
Yes.
Yay. Okay. Thanks. Thanks, Nick. Yay! Go, Nick.
Really enthusiastic for all of us. No one's allowed to make these
I'm gonna
sad.
go get my. I'll go get my plug in just a second. All right. So let's look at writing the Kc's for this first equation A. All right. Well, we've been doing it. So Kc is just the concentration of the products over the reactants. So for A, I have the Kc is going to be the concentration of carbon monoxide. And then times the concentration of liquid water?
Yeah.
Wait, does liquid water have a concentration? Actually, it does technically, but that's okay. Not really, right? And here's the other thing, right? In an equilibrium, we're going to see that these concentrations can change to maintain that constant, that they shift, right? Is water going to change its concentration? No, because it's a pure substance. Okay, so it has it's a pure substance. So if something is a pure substance, it doesn't enter into the equilibrium constant, right? So if it's a liquid or if it's a solid, it does not go into the equilibrium expression because its concentration won't change. Okay? So I'm not going to enter that into the reaction. And then I'm going to have the concentration of CO2 and the concentration of hydrogen. So that would be my equilibrium constant for that first equation. Right? So keeping that in mind, you guys write the second one while I go up and get my power cord real quick. All right, so guys, looking at that second one, hopefully you wrote Kc is equal to CO2 squared over carbon monoxide squared. Yes? Yay! Cool. All right, now I have a question for you. I'm full of questions. If we look back at this first expression, and in general, I guess my question is going to be, do equilibrium constants have units?
Yes.
No.
Because
Yes.
normal Ks have units, so why wouldn't these Ks have units?
Ah, good question. You want me to explain why they do not have units?
No, I'd like to
Equilibrium
keep believing
constants
that they
do not have units. Is this something you need to know? No. Okay, wait. You need to know they don't have units. You don't necessarily need to know why they don't have units. But I hate not knowing, so I'm going to tell you anyway. All right? But you don't have to know it. But you do have to know they don't have units. All right, so I think I'm repeating myself. All right, so this, even though we use the symbol for concentration and we use the value for the concentration, it is technically not a concentration. This value that we use in that equilibrium constant is actually known as an activity. Okay, it's known as an activity. What is an activity, you may ask? Well, the activity is the actual concentration of that component at equilibrium compared to that concentration as a reference. For aqueous systems, that reference is 1 molar. For gaseous systems, the reference is 1 atmosphere partial pressure. Okay? So since it's the concentration over a reference concentration, the units cancel. Activities, which are technically what's used in that equilibrium expression, do not have units then. Okay?
So the whole last unit has just been a big lie, and those actually aren't concentrations, they're activities.
No, well, they're a concentration compared basically to 1, because it's 1 molar and it's 1 atmosphere. So you still use the same value. What do you mean the whole last? No, those were concentrations in the kinetics unit. Oh, definitely were concentrations, yes.
Okay.
Yes. But now that we're using them in that equilibrium expression, they are technically
Oh,
activities.
okay, so it's just,
It's just the value of the concentration without units.
okay. that makes
Okay.
more sense.
Yeah. It always bothered me that they didn't have them. That's why
It's weird.
wanted-
It's
Yes.
Like
weird,
one less thing to keep track of.
All right, I don't think we need to. Nope, this is not the one I want. I'm going to have to find the next one. The reaction that we're going to find the Kc for is actually the overall reaction. So we're looking to find the value of Kc for this reaction. What kind of a problem does this look like? Kennedy? It looks like a Hess's law problem.
Yes!
Yeah, so we're going to combine these two equations to get to the overall equation. All right. So, what I'd like to start doing is, I have a value for my Kc. I want to quickly write what is the expression for that Kc for this first reaction. And it is the concentration of the products divided by the concentration of the reactants. Okay. So looking at this overall equation, I see the first component is HF. It only shows up one place in that first equation. Did I have to do anything to that first equation so that it kind of matches what the overall is? I have to multiply it by 2. Okay? So I have to multiply this equation by 2. Okay? So that when I add them together, I can get at least the 2HF. Now, when I do that, what does my Kc now become? So I'm going to now down here write my new Kc for that equation multiplied by 2. Well, I have my hydronium ion squared, my fluoride ion squared, and the concentration or the activity of HF squared. Shoot, I didn't just multiply that by 2, did I? What did I do? I had to take everything to the power of 2. Okay? So when I multiply an equation by a number, I'm going to take its Kc value to that power. All right? You guys with me? So this Kc gets squared. Okay? So, in my second equation here, what have I done? What did I do to make those two equations adding up add up to this next one? Kennedy? I did. I flipped it. Looking at this next, the oxalate ion C2O4 minus 2, I see that it's over here, so I had to flip it. When I flip it, what do I do to my Kc? Take the reciprocal, right? So to the -1 power. Now in Hess's law, I would just add those two equations, correct? And I get my overall. All right, well let's just real quick do the Kc for my overall equation and see what it is equal to. So here I get F fluoride ion squared times the oxalic acid over HF squared and the oxalate ion. One thing I forgot to do is say what this looks like after I flip it. So after I flip that, I get the oxalic acid, over H plus squared over C2O4 minus 2. You guys all with me with where I got that from? To go from these two equations, did I add them to get the overall? What did I do? I multiplied them. So when I add two equations, what do I have to do to the Kc's to get the overall? I have to multiply them together. All right. So did we cover a fair amount today? Yep. All right. The intent was hopefully to make things make more sense after you have looked at the screencast or at least read the book, what you were supposed to do. All right.